our section on experimental tests with the gravitational redshift. That won't take long. And then I want to tell you what we're going to do in this final week. So going backwards, this was labeled A in our list of experimental tests. And unlike the other tests, it isn't really testing Einstein's equations so much as the equivalence principle. So consider a clock. In an arbitrary gravitational field. In a locally inertial system, with coordinates psi alpha, the interval between ticks is d tau equal minus eta alpha beta d psi alpha d psi beta to the half. In an arbitrary coordinate system, x mu is minus g mu nu dx mu to the half. Now let's suppose the clock has velocity for velocity dx mu d tau, dt, I'm sorry. Then the interval between ticks will be given by dt by d tau equal minus g mu nu dx mu d tau dx mu d tau to the minus half. So
I'm used to seeing velocity as being a derivative with respect to tau. So whose coordinate is t, and the velocity is?
yes, this is the velocity in the coordinate system with time t. It's not the full velocity.
Is this the? So is t x not?
Yes, t is x naught, that's right. Correct. And I'm putting c equals to 1. So if the clock is at rest, dt by d tau equals minus g naught naught to the minus a half. And this is the origin of the statement. Clocks run slower in a gravitational field. Because the interval between ticks will be greater, when the gravitational field is present. Now, it's not easy to compare dt and d tau, but it's easier to compare the time dilation factors. At two different points. So we're going to consider light emitted at point 2 and observed at point 1. Sorry, it's a bit damp, this board. So dt1 equals d tau times minus g naught naught of x1 to the minus a half, and dt2 is dt minus g naught naught x2 to the minus a half. So if the gravitational field changes from x1 to x2, the rate at which clocks are slowing down will change. Now, in the weak field limit, g naught naught is approximately minus 1 minus 2 phi. So the frequencies, well, before I talk about let me make a comment about the frequencies of the light. Frequency of the light emitted at point 2 divided by its frequency received at point 1 will be the ratio of g naught naught at x2 over g naught naught at x1 to the half. So now we're getting to something we can measure, because in this limit, nu2 over nu1 will be 1 plus delta nu over nu, and delta nu over nu will be phi of x1 minus phi of x2. The other way around, x2 minus x1. So if we're on the surface of the Earth, for example, we can measure the frequencies and calculate the time dilation factors. Now this was carried out by Pound and Rebka some years ago. With a terrestrial experiment. So this was Earth. And they looked at the frequencies in a 40, just to give you the I'm sorry? Bit bigger, yeah. Absolutely. You can read that one, can you? Right. So, two physicists by the name of Pound and Rebka did a terrestrial experiment. And if you want the technicalities, they looked at an iron atom, Fe57, and looked at the 14.4 keV transition. So there's some photons associated with that, and they measured the frequency at one point and at another, and the fall was actually quite short, 22.6 meters. And the predicted value, according to Einstein, is delta phi is minus 2.46 times 10 to the minus 15. And the experiment was delta phi minus 2.57 plus or minus 0.26 times 10 to the minus 15. So once again, it's all consistent with Einstein. It would be nice if there was another test done recently to do with gyroscopes orbiting the Earth, which again confirmed Einstein. It would be nice if we had other tests, since it is such an important theory. But the only place you might say, do we doubt Einstein's theory at all, given all this experimental tests? And I suppose there's two regimes where you might call it into question. One is on the very large. If we believe Einstein's theory, then we have to invoke dark matter to explain the rotation of the galaxies and what we observe. And that's the conventional view, that there is dark matter. On the other hand, we haven't found it, we haven't seen it. And so an alternative viewpoint might be to say, well, maybe it's Einstein's theory that needs to be modified. And that debate continues, but the conservative view is that Einstein is right, and we just have to keep on looking for that dark matter. The other regime where we'd call Einstein's theory into question is on the very small, when we attempt a quantum theory of gravity, because if you apply the usual rules of quantum field theory to Einstein's theory, they don't fit together. And we need something that goes beyond quantum field theory, like string theory or something, some other alternative. However, we have no empirical evidence that Einstein's theory goes wrong at that scale, simply because it's 40 orders of magnitude weaker than the other forces, and so it's very difficult to get experimental handle on that. So that concludes our section 3 on experimental tests of Einstein's theory. And I now want to tell you what we're going to do for the rest of this week. Are there any questions on section 3 before we move on to section 4? Yeah?
Maybe could you explain why G not is less than 0.5?
Okay. I may have made a sign error. You never know. It's not. In metric, our metric was 1. So G naught naught starts out as -1. And in a gravitational field, it's -1 minus 2m over r. Yeah. So this is -1 plus 2m over r. So minus G naught naught is 1 minus 2m over r. So in the gravitational field, G naught naught will be less than 1. You can think of that as being like a refractive index, if you like. Light traveling through a gravitational field is slowed down, just as it is when it passes through a piece of glass. So in the rest of the week, we're going to be doing two things. Section 4 will be the Lagrangian formulation. In 1916, the same year that Einstein wrote down his field equations, the mathematician Hilbert, of Hilbert space fame, amongst other things, derived Einstein's equations from a variational principle. In other words, he wrote down a Lagrangian and derived Einstein's equations as the Lagrangian equations of motion. Curiously enough, in 1923, Wolfgang Pauli of Pauli matrices and the exclusion principle fame complained of Hilbert that his presentation, though, would not seem to be acceptable to physicists as opposed to mathematicians, for the existence of a variational principle is introduced as an axiom. Well, that's strange to hear Pauli say that, because nowadays it's the other way around, and most physicists would be unhappy with any field theory that wasn't derived that way from a Lagrangian. In fact, when physicists talk about a Lagrangian and they talk about a theory, the two words are more or less interchangeable. What's your theory? What's your Lagrangian? So things have changed since 1923, and nowadays when one physicist tells another about his theory, he or she writes down a Lagrangian. So we're going to be showing how Einstein's equations and the equations of the other fields that gravity is coupled to follow from a Lagrangian, or more precisely, an action, which is the integral over all space of a Lagrangian density. So the first thing we need to do is talk about integration of tensors. Once we know how to integrate, we can write down an action, and we can derive Einstein's equations by varying the action and deriving them as the Lagrangian equations of motion. Now, it turns out there's two ways of doing this. One is called the first order formulation, the other is called the second order formulation. The conventional one is second order, but I want to briefly mention the first order. The fundamental variable in gravity is the metric tensor G mu nu, and the Christoffel symbol gamma mu nu rho is written in terms of the metric and its first derivatives. So it's a derived quantity. In the first order formalism, you take a different point of view. You say, let's regard G and gamma to begin with as independent variables unrelated to one another. One's got two indices, the other's got three. And you write down a Lagrangian that depends on G and gamma, and you treat them as independent variables. And you find that the G equation gives you the Einstein equation, but the gamma equation tells you how to relate G to gamma. And so you get back with the same expression that you had before, gamma as a function of G, but this time it emerges as an equation of motion rather than a definition. And that has some advantages, some disadvantages over the conventional approach, but it's worth mentioning. Now, the Lagrangian formulation facilitates a discussion of what sits on the right-hand side of Einstein's equations, which is the all-important energy momentum tensor. We'll have something to say about that. And the Lagrangian also facilitates the discussion of the relation between symmetries and conservation laws. Actually, that's 4.6. 4.5, I'll do what I've been promising to do and tell you exactly what Rands-Dicke theory is, which is a variant of Einstein's theory, which is interesting more by providing a comparison with Einstein rather than its intrinsic merit, because it's been more or less discredited. But to understand the right theory, it's often good to compare it with wrong theories. You learn something that way. Now, the universe is made out of bosons and fermions. And for most of the 3 weeks, we've been talking about bosons. So we're missing half the universe. And I want to try and remedy that just briefly anyway, by talking about the Vierbein formalism, because that enables you to talk about how gravity couples to fermions. And I'll briefly mention it, though we won't dwell on it. Supergravity, which is a theory of gravity coupling to fermions. So that's an important component in the general theory of relativity, is to write down the Lagrangian and how it couples to other fields. And that's essential for any attempt at a unified theory that goes beyond Einstein's theory. And then finally, we're going to talk about cosmology. And I'll begin by summarizing what is the standard in inverted commas model of modern cosmology, which goes by the name of lambda CDM model. The lambda stands for the cosmological constant, and the CDM stands for cold dark matter. And just as we have a standard model of particle physics that is taken as the paradigm by which to judge all other theories, so there's a standard cosmological model which has emerged over the last few years. Doesn't mean it's right, but it's the benchmark by which we compare other theories. But we want to focus more not on the astrophysics, because in any case I'm not qualified to go into the details of the astrophysics, but so that's 5.1. 5.2 is how does general relativity enter this depends on a combination of astrophysics observation, astrophysics theory, and general relativity combined. And our focus will be on the ingredients that are coming from general relativity. And this will involve the famous Robertson-Walker metric, on which all cosmological models are based. And more specifically, that's more or less, if you like, the kinematics. The dynamics comes from Einstein's equations and from solutions first found by Friedmann, which form the basis of the expanding universe models of cosmology. So that's what we've got to get through. Let's start with 5.1 integration. 4.1. Now, we could spend a lot of time doing differential forms, but I'm not going to do that because we don't have the time. But I'll mention some brief results, some with proof, some without. Now, we recall, because we've already discussed it, that what's sometimes called dv, or equivalently d4x, which is the product dx0, dx1, dx2, dx3, is not a scalar. Rather, it's a scalar density of weight minus 1. So that means dv prime was dx prime dx dv. For example, in going from Cartesian to polar, we find dx0, dx1, dx2, dx3 is r squared sine squared theta dt, dr, d theta, d phi. But the square root of minus g transforms like a scalar density of weight plus 1. And root minus g in polar coordinates, in Cartesian coordinates, is equal to one in polar is equal to r squared sine squared theta. That was just an illustration of Minkowski space written in polars versus Minkowski space written in Cartesian. But in general, we're going to be interested in curved space. If we have a scalar phi of x, in order for the integral to be invariant, we don't integrate d4x, but we integrate d4x times the square root of minus g. So that's the trick, basically, for getting Lagrangians and quantities that transform in the right way under general coordinate transformations is that you don't integrate d4x, which is a scalar density, but d4x square root minus g, which is a scalar. Now, that's integrating overall space. All, when I say all space, I mean all four-dimensional space-time. But we're sometimes interested in integrating over a submanifold. Manifold here is a mathematical term that we won't get too precise about. I'm using it interchangeably with space. Sometimes we want to integrate over a subspace of the four-dimensional space. Now, how do we parameterize a subspace? Well, we write our four coordinates, x mu, as a function of u1, u2, up to up, where these are the coordinates of the subspace. So P could be anything less than or equal to 4. Could be 4, 3, 2, 1. So we want to form quantities that transform in the right way. And it's useful to introduce what I'm going to call d tau, where the indices go from mu1, mu2, all the way up to mu p. I could call them mu nu rho sigma lambda, but I prefer to call them mu1, mu2, mu2, so on. And this is going to be related to the volume element on the subspace. And the way we relate it is to take dx nu1 du1 dx nu2 du2 all the way up to dx nu p dup. And then we put in this generalized Konecker delta that we introduced earlier, which has indices mu1 to mu p upstairs and mu1 to mu p downstairs. By construction, this is a scalar under u goes to u prime of u, and a tensor of rank p under x goes to x prime of x. So if T mu1 to mu p is a rank p tensor, now it's an antisymmetric tensor. It's antisymmetric. Well, I'm telling you it's antisymmetric. And it's sometimes called a p-form by mathematicians. Then T contracted with d tau is a scalar. Under both u goes to u prime and x goes to x prime. So this is taking us where we want to be, because this means that the integral over V, which is a volume, a p volume of T mu1 to mu p d tau mu1 to mu p is invariant. Now, depending on the value of p, this would be called a line surface 3-volume or 4-volume integral. Yeah? This one? Why is this tensor? Tensor of rank p under x goes to x prime of x. Sorry, I'll write bigger. Is there anything else you want me to write bigger? Can you read it? So, armed with this, we can now state Stokes' theorem. And it says if we integrate over some p plus 1 volume, d tau mu 1 up to mu p plus 1. Can you read that? D by dx mu subscript p plus 1 of the tensor mu 1 to mu p. This is the integral over the boundary of that volume, which we call Vp, d tau mu 1 mu p t mu 1 mu p, where Vp is the boundary of Vp plus 1. Now, this is all very general. Of particular interest is the case of 4 dimensions, of course. So let's take 4-dimensional space-time, which is the case p equals 3 in this example. Then tau mu, which is 1 over 3 factorial epsilon mu nu rho sigma tau mu rho sigma equals root minus g t mu is a density that's the definition of T mu of weight plus 1. Then the integral dv d mu root minus g t mu equals the integral. This symbol means the boundary of this volume V, root minus g t mu ds mu, where ds mu root minus g equals 1 over 3 factorial epsilon mu nu rho sigma d tau mu rho sigma. And just to make that more explicit, dv means this, ds mu means it's a 4 vector, and the entries are dx1, dx2, dx3, dx0, dx2, dx3, dx0, dx1, dx3, and dx0, dx1, dx2. So that's just some formalism that we need. We won't need all of it, actually. Just Stokes' theorem is all we need. need that to do what we want to do next, which is to get Einstein's equations from a variational principle. So we're looking for an action which we call S, which is a function, or strictly speaking, a functionale of the function g mu nu. So I put square brackets to say that it depends on g. That means in practice it's an integral of a Lagrangian density that can depend on g and derivatives of g. But the idea is that if we vary g, the resulting variation in the action is 0. And delta S equals 0 gives us the field equations. General covariance requires S is invariant. Under general coordinate transformations. And we're going to insist insist is too strong a word. Why do we insist on no more than 2 derivatives? Well, that's because we know the answer to some extent. We want to have second-order differential equations. But
what exactly do you mean when you say insist on no more than 2 derivatives? Insist that no more than 2 derivatives if you're where, or what contains no more than 2?
We don't want to have more than
the expression for what?
the action. I'll show you what I mean by that right now, as a matter of fact. It's got to be the integral d4x square root of minus g times a scalar. And what scalars do we have at our disposal that are built out of g? The only one is the curvature scalar. Now, there are other scalars we could form. For example, these are scalars, but they involve more derivatives. So we don't want to have third derivatives, and we don't want to have first derivatives more than squared. There is another term I could add with the cosmological constant. I'll come to that in a moment. But let's forget the cosmological constant for a moment. Why does this give us... This, incidentally, is the one that Hilbert wrote down. And it's sometimes called the Einstein-Hilbert action. And these notes were taken from Anderson, so I'm putting -1/2 kappa, where kappa is -8 pi g. The normalization, for pure gravity, the normalization is irrelevant, actually. The normalization will be important when we come to couple gravity to matter fields. Let me just see if I've, by definition of kappa, yes. Okay. Now, we want to show that this gives us the right equations. So what we're going to do is an infinitesimal variation. By an amount delta G mu nu. Now, delta root minus GR is what we want to compute. But R, you remember, is itself G mu nu times R mu nu. So this can be written as root minus G R mu nu delta G mu nu plus R delta root minus G plus root minus G G mu nu delta R mu nu. Just use the Leibniz rule. Now the hard part is delta R mu nu. But we get that from its definition as the contracted Riemann tensor. And we can write it in terms of delta gamma. we write out the Riemann tensor in terms of gamma and contract it to get the Ricci tensor, then that's what you get. But now we have to write delta gamma in terms of G. Which is minus G lambda rho delta G rho sigma gamma sigma mu nu plus 1/2 G lambda rho into d nu delta G rho mu plus d mu delta G rho nu minus d rho delta G mu nu. Yeah. Okay. Yes. That eta mu lambda kappa eta. Thank you. That's the right one. Now, we can write this as a tensor. It's interesting that gamma is not a tensor, but delta gamma is a tensor. And it involves the covariant derivatives of delta G. And once again, the covariant derivative of G is 0, but the covariant derivative of delta G is not. So delta gamma is a tensor. Delta G mu nu semicolon rho. This is going to simplify in a moment. So the variation of the Ricci tensor, mu kappa, can be written as the variation of gamma, mu lambda lambda semicolon kappa minus delta mu lambda semicolon lambda. Now we can rewrite that. We're getting to the answer we want now because we can rewrite that in terms of the metric delta G lambda rho semicolon mu semicolon kappa minus delta G rho mu semicolon kappa semicolon lambda minus delta G rho kappa semicolon mu semicolon lambda plus delta G mu kappa semicolon rho semicolon lambda. So that's the hard part. The other part we need is delta G delta square root minus G is 1/2 square root minus G, G mu nu, delta G mu nu. And delta G mu nu upstairs is minus G rho mu G nu sigma delta G rho sigma downstairs. So we can collect these results together and write the variation of the Einstein-Hilbert action But this term, from what we've written before, is the derivative of something, the ordinary derivative of something. It's the ordinary derivative of delta gamma lambda mu lambda minus the ordinary derivative with respect to lambda of G mu nu delta gamma lambda mu nu. This is what physicists call a total divergence. So if we now use Gauss's theorem or Stokes's theorem, whichever was, they're both special cases of that general surface integral I wrote down. When we integrate over all space, for variations that vanish on the boundary. Now, if there are any experts in the audience, you might say, what about the Gibbons-Hawking term? We're not going to worry about it. We're going to assume that the variations vanish on the boundary, which is what Hilbert did. And you see, it's all simplified to something rather nice. The variational principle, which requires the variation to vanish, has yielded the empty space Einstein equations. So next time we'll show how that gets modified when we add a cosmological term and when we add matter fields. And we'll also talk about first order formalism. Are there any questions on what I've just done? This is how all field theory is done nowadays with Lagrangians, not with equations of motion. So getting used to the Lagrangian formulation is an important piece of your education. Yep. The 1.5 order formalism. Probably not. I mean, I'll spend the most 5 minutes on supergravity. And I might mention it then, but no.
Are you now using Emerson resource more than number?
Yes, good point. I'm now, we will in section 4, and to some extent section 5, go beyond Weinberg.
Will be what Weinberg?
We'll be covering material that is not in Weinberg. Most of it will be, but there'll be some that isn't. This part is in Weinberg, I believe.
What's the user? What's the user significance of the total derivative?
The significance
total
of
divergence.
the total divergence.
Isn't something
If we have a Lagrangian that changes by a total divergence, then the action will be 0.
I'm sorry.
Part of the variation, the part of the variation that's the total divergence will integrate to 0. So having a Lagrangian that changes by a total divergence is as good as having a Lagrangian that doesn't change at all. They both give us